Hello, I hope you're doing well. This is section 6.5 of Calculus 3. So section 6.5 deals with two concepts. These are rather easy concepts. These are called curl and divergence. So this will be a brief presentation on the curl and divergence of a vector field, primarily in three-dimensional space. So let's get to that. Now, before I share my notes, I want to share a part of the textbook and we'll make some comments. All right, so let's get started. All right, so this is page 744 of our textbook by OpenStax. I think I mentioned this at the beginning of the semester, but this book is written by a well-known professor at the Massachusetts Institute of Technology, and the text itself is very well written as an exposition of calculus. So I highly recommend that you actually read this book. I know I'm saying this like well into the semester, but it really does help you to read the book. All right, so in this brief section, we have the divergence and curl. So first, what is divergence? Okay, and the author has a very good description of what the divergence describes. The divergence at every given point, it turns out to be a number, a scalar. So it is a scalar based function, and it is basically describing the outflowingness of the vector. The divergence of f at point P measures the net rate of change. So maybe you want to highlight this. The divergence of f at any point P measures the net rate of change with respect to time and the amount of fluid. So if f describes the motion or the flow of a gas or a fluid or some sort of energy, the divergence measures the tendency of the fluid to flow out of P. So if more things are flowing out than coming into point P, then the divergence would be positive. All right, and I'll describe what that means in this lesson. The next thing in this section is there are only two things in here. Okay. And after the author describes divergence, the next thing he describes is the curl of a vector space F. This is at the bottom of page 749, the second operation. And read what it says. The curl of F at point P is a vector. So this will be a vector valued function. It's, divergence is a scalar based or real valued, whereas the curl of f is a vector valued function. The curl of f at point P is a vector that measures, watch this, the tendency of particles near P to rotate about the axis that points in the direction of this vector. So you calculate what is called the curl. And maybe another better way to do this is this. He says, in other words, okay, the curl at a point is a measure of the vector field spin at that point. So imagine, okay, and this is a good analogy. Imagine placing a paddle wheel into a fluid at P. Okay, so think of a paddle wheel. Put this right in the middle of this space on which F is defined. And what happens is it's going to start turning so that this axis will be the axis about which the rotation is most optimal or most prevalent. Okay, and once this is set, the paddle wheel will start to rotate in a certain direction. Right, and so the spin or the tendency of the paddle wheel to rotate in the direction defined by this vector, which is the curl of f. Okay, the direction of the curl is the direction in which the rotation about that axis is the most prevalent. Okay, and then the actual tendency of this object or this fluid to go around the axis, that is the magnitude of this vector called the curl. Okay, so keep this in mind. You don't have to understand this fully because it is a fairly complicated concept. But if you keep this in mind, especially this visualization with a paddle wheel, that may help you understand this concept of curl. All right, now with that, let's go to our notes. Okay, so section 6.5 is on divergence and curl. let F be P, Q, R, a three-dimensional vector field, okay, as before. Let's specify a vector field, and it's defined on every point of, R3, X, Y, Z, right? So number one, the curl of F. Okay, I'm going to do the curl first, even though the book has the divergence first. Okay, curl of F, abbreviated, well, not really abbreviated, CURL of F. Okay, this is, it's rather tricky. Let me tell you what it is first. Okay, it is R, the partial of R with respect to Y minus the partial of Q with respect to Z, comma, pz minus rx, comma, qx minus py. And you say, what in the world is this? It's, how do you even expect us to remember this? Good um, good point. Okay, it is a vector field, first of all. All right, you have three components here, right? First, second, and third. Now, how do you remember this? And what in the world does this signify? I kind of described what it signifies. It describes the tendency of F to rotate about this axis and so on. But the way to think about this and the way to remember this is this. It's very much like that cross product. You have IJK, it turns out to be a sort of like a 3 by 3 matrix. And then the second row would be not a vector, but this is called the partial operators, okay, the gradient operator. Our partial with respect to X, with respect to Y, with respect to Z, and then you put P, Q, R in here. Now, what does this mean? Okay, this means first, you have this I. Let me go ahead and write this. You take this I, and then you do a 2 by 2 matrix here. This minus this. Okay, so what does that mean? It's a partial of R with respect to Y minus the partial of Q with respect to Z, right? And then you put I in here. The next one is tricky, as you know, right? It's going to be minus, okay, minus this, minus that. So what does that mean? Minus R, so let's be consistent here. It's a partial of R with respect to X. That's what this means. Minus partial with respect to Z of P. Okay, and then you put J on here, and then plus, then the last one would be this minus that, right? So that means partial of Q with respect to X minus the partial of P with respect to Y and K. So that's what this is. But really, I mean, first of all, I don't like this IJK notation as much as the bracket notation. And second, instead of writing, with this partial notation, why don't we just write this as ry minus qz, comma, and then because of this negative sign here, negative sign here, I can write this as pz minus rx, comma, and the last one is qx minus py, and this is our gradient, our curl of f. Right, because this is very much like the cross product, right? Cross product. It's not the cross product because the cross product is only defined between two three-dimensional vectors. And what I'm saying is this thing, the second row is really not a three-dimensional vector, okay? It is an operators though, okay? So we call this the gradient operator. What is the gradient operator? Well, gradient operator is not a vector, but it is like a command or an instruction. It's an operator, like the derivative operator. This is telling you, hey, you are to take the derivative of, this is called the derivative operator, because whatever comes after that, this is commanding you, telling you to take the derivative of this, okay? So what gives you an instruction as to what follows is called the an operator in mathematics. And so this upside down triangle is an operator called the gradient operator. And it says, take the rate gradient of what follows, okay? In this case, what follows is the curl, or each of these components of the vector field F. All right. So because this because the second row is the gradient, let me write this down, gradient operator, and the third row is the vector field f, right? So often curl of f is written as the gradient operator cross f, because it is like the cross product of the second row and the third row. Okay, so if you see this, this doesn't mean anything magical or anything, like a secret code. All this says is the curl of f is the gradient operator with the cross with f, even though it's not a cross product. It looks like a cross product. And so this is a way to, this is a great way to remember how to calculate the gradient, how to calculate the curl of the vector field f. All right. So again, it describes, maybe I should tell you, this describes the tendency, okay, axis about which, that's supposed to be a W, about which f rotates. Okay, so it'll give you a vector. So at any point p, well, at any point x, y, z, let's not use p because I have used capital P to mean the first component of f. So at any point x, y, z, okay, if you calculate the curl of f, what it's going to give you is some vector. Okay, and what this is saying is this is the axis about which the object, gas or fluid, tends to move around this axis the most. And the length or the magnitude of this curl tells you what that tendency is for the fluid to go around this thing. Okay, so that's all I'm going to say. And let me go ahead and define the second one as well. Number 2, the divergence of f, divergence. Okay, and so this is abbreviated div of f. Okay, and this is a much easier one. If f is pqr, the divergence is px plus qi plus rz. Okay, so it's in the same order, pqr, okay, xyz. So you just take the partial of the first component with respect to the first variable x, second component with respect to the second variable y, plus the third component r with respect to the third variable z. Sometimes people write this as dp dx plus dq dy plus this is not really d, partial of r with respect to z, right? Now, it is not a vector. It's not a vector. It is a scalar function, or you can call this a real valued function. Make sure you know it's not a vector. All right, but it looks very much, I mean, notice here, this is like, if gradient is, remember the gradient operator is, take the partial with respect to x, partial with respect to y, partial with respect to z, and f, the vector field is, remember it's p, q, r, right? So it looks like the gradient, the divergence of f is pretty much telling you to do what? It's like the dot product of, see that? It's like the dot product of this gradient operator with f. After all, it is the parts, you take this and differentiate this with respect to x, differentiate this with respect to y, differentiate this with respect to z, and add them. Okay, so the abbreviation, or another way to denote the divergence of f is the gradient operator dotted with f. So this is another way where people see that. Very much like the curl. Curl is the cross product, and the result is, not surprisingly, a vector. The divergence is the dot product, and not surprisingly, the result is a real valued function. Okay, so those are really the two main things. All right, and maybe I should say this represents the amount, net amount of f flowing out of the point P. All right, so if you have a vector field like this, if this is a vector field, at this point, the divergence of f is going to be positive. Okay, you see, because these vectors coming out are bigger than the ones coming in. And if f is, let's say f is a constant, well, I just should have just 1 point. Okay, if f is just a constant function, maybe f is 1, 0, and at every single point it's 1, 0 or 1, 0, 0, and it always flows like this. So the same amount is flowing in as flowing out. In that case, the divergence will be 0 at that point. And by the way, it is the number 0, not the vector 0. Okay, if at some point f has what we call a sink. Okay, if everything is coming in here and very little is going out or nothing is going out, then the divergence will be negative, because remember, the divergence is measuring how much is flowing out of the point. Okay, so this is pretty much all you need to know for this section. Now I am going to give you some examples to just make sure you understand these things. Here is our example vector field: xy, negative y, xz. Okay, let's find the divergence of f and the curl of f. First, the easy one, divergence. Okay, all you have to do is to take the partial of the first one with respect to x, and the partial of the second with respect to y, and the partial of the third with respect to z. You don't even have to write this line here because it's pretty obvious if you know what the divergence is. So what is the partial of xy with respect to x? Well, that's simply y. And for this one, you'll get negative 1. And for this, you get just plus x. Very simple, right? So that's exactly what the divergence is. Now the curl of f, you have to do a little more work because it's ijk, partial of x, partial of y, partial of z, and you write xy, negative y, xz. All right, and then you do just like what you did for the cross product. It's this minus that. What is that? Well, if you take the partial of xz with respect to y, you get 0. And if you take the partial of negative y with respect to z, that's also 0, right? So the first part is like that. The next part, you do negative of this combination minus this combination. Now this first combination is the partial of xz with respect to x, so you get z. And for this one here, you take the partial of xy with respect to z. Well, that's 0. Okay, so that is the middle factor. And then the last one will be this minus that. Okay, so the first one is you take negative y and differentiate it with respect to x, you get 0. And the last one is you take xy and differentiate it with respect to y, which is x. All right, so the answer will be 0, negative z, and negative x. This will be the curl of f at any given point, x, y, z. All right, so it's not difficult to find these things, right? All right, maybe we can do another one. Let's do something a little more complicated. X squared y, y, and then y plus e to the z. Okay, what is the divergence? I don't think I'm going to skip the definition part, right? So all you have to, oh, by the way, I made a mistake already. Did you notice the mistake I just made? Okay, I put divergence of f equals to, and I put this bracket. I shouldn't have, right? Because divergence is not going to be a vector, all right? So even just having this, I should stop and repent and say, okay, undo, all right? So what is the partial of this with respect to x? That's 2xy. What's the partial of this with respect to y? It's 1. What's the partial of this with respect to z? That's e to the z. Okay, that's it. It's that simple. Okay. Oh, by the way, why are we learning about divergence? Well, because we will be using this idea, divergence, in the divergence theorem section, of course. Right. And how about the curl? Okay, now the curl is again more complicated. You do I, J, K, partial x, partial y, partial z, x square y, y plus e to the z. All right, I like to have brackets and I do this minus that. Okay, and you can easily see that it's going to be 1 minus 0 for the first one. For the next one, I always try to do this, negative and then parentheses. It's going to be this minus that. Well, the first one is the partial of this thing with respect to x. Well, there's nothing there, so that's going to be 0. And then this other part here will be the partial of x squared y with respect to z, and that's also 0. Okay, you see that? And then finally, you have the partial of this y with respect to x, and then partial of this with this x squared y with respect to y, and that's x squared. So the answer, 1, 0, negative x squared. And so that would be the result. So this is really easy, right? And so there's really not much more in this section, except this one theorem I will be describing here in just a second. All right, so here's a quick theorem, and this is an interesting one for any vector field F, which is written, three-dimensional PQR. Okay, it turns out, maybe I should write this in red. The divergence, not of F, but if you take the curl of F, remember, which tells you which direction and how much of the tendency of rotation you have of F at a given point. If you take the curl of F and take the divergence, you always get 0. Oh, sorry, it's not the vector 0, it's a number 0. Okay, and that may sound strange. That this is true for any vector field PQR and any point XYZ. So that may sound a bit surprising, but it's really not. Okay, and the proof is actually pretty simple as well. So let me go ahead and do this. All right, so that we're talking about the divergence of the curl of F. Okay, so the divergence of the curl, that doesn't look like curl of F. Okay, so the divergence of the curl of F. All right, what is that? It's the divergence of course, I, J, K. And the middle one is, the second row is the gradient operator. And then you have P, Q, R, right? And so what is that? It's the divergence of this vector field, which is Ry minus QZ, comma, and then you have PZ minus Rx, or negative of Rx minus PZ. And then the last one is Qx minus Py, right? This is just a definition of the curl. And if you take the divergence, okay, what do you get? This is going to be R. You take this first one and then differentiate it with respect to x. So it's Ryx minus QZX. The second one with respect to y, so PZY, oh, that's going to be a plus. Okay, remember, we're talking about the divergence. Plus PZY minus RXY. All I'm doing is putting a y right after this, like this point and this point. And then finally, plus QXZ. Remember, we're trying to differentiate this with respect to z. So it's QXZ minus PYZ. All right, but if you look at this, you remember the mixed partials are equivalent or equal to each other. For instance, you have R, YX, and you have RXY. They cancel each other. And you have negative QZX and positive QXZ. They are the same, so they cancel each other. And then you have PZY and negative PYZ. They also are equal to each other, so you get 0. All right, that is fascinating. Okay, well, unfortunately, this is fascinating and not very useful. So this is a great result. Okay, but we probably will not be using this very much. Okay, so one last quick thing here. What if F is two-dimensional? Okay, well, then the answer is you just kind of add, so think of just this as two-dimensional vector field, a two-dimensional vector field embedded in the three-dimensional space. So you just sort of add this zero as the last component, okay? And that's how you can calculate this. For instance, you can talk about the divergence of this as, what is that? Px plus qy plus zero. Well, then this just becomes px plus, sorry, this is y, okay, qy. All right, now if you remember, and this is the sort of a crucial element in here. If you remember, in Green's theorem for the flux integral, you remember you had the double integral of what? That was px plus qy dA. And this was the right-hand side of Green's theorem part 2, which is Green's theorem for flux integral, right? So I mentioned back then that what you're integrating turns out to be the divergence of f. This is important in the sense that if you extend it to the three-dimensional vector field, this pretty much becomes what we know as the divergence theorem. Okay, so that is why I am explaining this. All right, and then what is the curl of f if it's PQ0? Okay, well then you have IJK, you still do the same kind of thing here, and then on the bottom you just have PQ0 if f happens to be two-dimensional. Okay, so you're thinking of this even though everything here is depending on your two-dimensional vector space, which is two-dimensional space, which is the plane. And remember, you have this curve C, which is the boundary of the region R. Okay, so far nothing is nothing is three-dimensional in this particular F, which is just PQ. I am just adding this zero at the end, PQ0, just so that it makes sense to talk about the cross product. Okay, and so here, try to calculate this. It's going to be zero. What? Yeah. Oh, by the way, this is going to be zero as well. Okay. Why is that going to be zero? Because there is nothing in the third dimension. Okay, there is nothing in terms of z, so that's going to be zero. Okay, so let's go ahead and put zero in here. So you see what happens here? It's going to be zero minus zero. That's zero. Okay, and then for the second component, it's going to be this. Sorry, negative of this minus that. But again, it's going to be the partial of zero with respect to x minus the partial of p with respect to nothing, right? So that's going to be zero. And so what really matters is only the last component, okay? And the last component will be qx minus py. You may have heard this before, qx minus p. And so if you visualize this vector, okay, so this is the curl of f in case f is two-dimensional, right? So it'll be standing up because the first two components are zero, and only non-trivial component is the third one, which means this goes in the direction of the z-axis. So this is py qx minus p. All right, so what this means is the curl of f turns out to be just a vertical vector. But typically, we just write this as 0, 0, and then qx minus p. And if you remember, in the first Green's theorem statement, and that's the Green's theorem for work or circulation, the right-hand side was the double integral over R of what? Qx minus p, right? So this was the real valued function, which happens to be the third component, the only non-trivial component, the one that goes up in the vertical direction of the curl of f. So this, you are basically integrating the curl of f, where f was two-dimensional. And as you do so, the magnitude of this thing is, of course, qx minus py, and that was how much it's turning around it. Remember I showed you in the proof of, or the rough proof of the Green's theorem, I'm talking about like each point, and then you have this thing called qx minus py. That turns out to be the curl of f, which is how much it's going around this, how much of the fluid is going around this, the boundary of the rectangular region. And the same thing here. same thing here, same thing here. And if you integrate it, in on this uh, region R, then what happens is every internal edge gets canceled, and the only thing that's left is the work around the outer bounds, okay, or the bounds, which is a curve C. And so that is used as a proof or the rough proof of Green's theorem. Right? And so this first one turns out to be the divergence of F, which gives you, which we will extend to the divergence theorem. This turns out to be the curl of F, and there is a three-dimensional version of this, which is the next theorem we'll be studying, called Stokes' theorem. Okay, so that's why these things are important. And I think that's about it. Should I give you another part of this? Yeah, I'm going to maybe give you another small, a short segment, giving you illustrations of very simple and maybe 3 examples to see exactly what the curl and the divergence means. All right. So the next part of this video will be just 3 quick examples to show you what the curl and the divergence means.